quasi-particles or phonons are the same?
Yes, yes, phonons of course quasi-particles too are associated with collective excitations associated with with the motion of ions in a crystalline lattice with respect to their equilibrium position.
Yeah.
So
what we are talking about quasi-particles, yeah. Are there phonons or are they different? No, you mean that phonons are quasi-particles?
yeah, there are many different quasi-particles. Some of them are described by fermionic statistics, some of them are described by bosonic statistics. So the quasi-particles subject to fermionic statistics in Fermi liquid are electrons and holes, or particles and holes. Quasi-particles associated with the lattice vibrations are phonons. Quasi-particles associated with magnetic, with the propagation of spin waves in magnets are magnons. The quasi-particles in charged electron-ion plasma are plasmons. So they are all quasi-particles. And the main subject of this course is to present the theory of many-body system in terms of collective excitation. So you may ask me what's collective in Fermi system, what kind of collective properties, why we are talking about collective properties. But the presence of Fermi C is already a collective property. I mean, we are discussing, well, last time we discussed a bit thermodynamical properties. Today we will discuss two types of magnetism in this system. Just in the case when you don't have a single electron, but you have Fermi C of electron. So the existence of this Fermi C leads to interesting phenomena, and we are about to discuss them. So next week we proceed with bosons. I spent 3 or 4 lectures on Bose-Einstein condensation, superfluidity, and excitations in bosonic system, which again will be sound-like excitations phones. Yeah. Okay. Then the subject of today's lecture is magnetism in electron systems. Electron systems. So the first part of this lecture, number 1, will be devoted to Pauli paramagnetism. And we use the properties of integrals with the Fermi distribution function, which we discussed last the day before yesterday. I spoke with Professor Müller and discussed with him what was said to you in course of advanced statistical mechanics about fermionic system. He assured me that the specific heat was discussed in many details, and therefore I decided not to touch this question in the lectures. We probably shift it to tutorials if you need to repeat this structure of derivation. And maybe on tutorials we also touch upon thermodynamic properties associated with phonons, what the specific heat. If you tell me that you didn't discuss thermodynamics of phonons in the statistical mechanics course or in solid state physics, did you?
Did it, but not in very detail.
Okay, then we probably shifted to tutorials, because what I also realized, speaking with my colleagues about your courses, that the missing part of your lectures in HTP is kinetic properties. So actually, as far as I understand, nobody taught you about kinetic at all. And therefore, I would like to discuss in 2 or 3 lectures transport properties in the metal, so electron transport, conductivity, thermal transport, thermal conductivity. Maybe we'll also discuss Hall effect and quantum Hall effect when we discuss strongly correlated physics, because my impression is that this is missing part of the topics covered in the lecture. Therefore, okay, but Pauli paramagnetism, as far as I know from Professor Müller, has also been discussed a little bit, but for consistency with the second part of my today lecture, when I will discuss Landau diamagnetism, I need to briefly remind you what Pauli paramagnetism is. Okay, and this is very simple. One doesn't need to calculate much, unlike diamagnetism, where we proceed today with some serious calculations. What do we have? We have electron gas in magnetic field. And usually one may ask question whether magnetism is quantum phenomena or classical phenomena. And the answer is of course, magnetism is quantum phenomena. There is no magnetism at all in classical physics. Why? Because the Pauli paramagnetism, which we discuss right now, as you will see, is associated with spin of electrons. So spin is affected by magnetic field, and since spin is an intrinsically quantum number which doesn't have any analogy in a classical system, that kind of magnetism which we discuss now doesn't have anything to do with classical properties. The second part of the lecture will be devoted to Landau diamagnetism associated with orbital motion of electron. And again, in quantum mechanics, in contrast to classical one, the energy spectrum of the particle moving in a magnetic field, now I'm not speaking about spin, is discrete. And this discreteness of spectrum is at the heart of quantum properties, existence of Landau levels, and this again will lead to quantum effect, and we discuss both of them on the equal footing. So what we will calculate today? We will calculate for both cases paramagnetism, and let me write it, number 2, Landau diamagnetism. We will calculate magnetization of electron gas subject to magnetic field due to existence of spin and due to the existence of orbital motion, and we will calculate susceptibility of the electron system. Okay, let's start with Pauli paramagnetism. So as I said, in quantum mechanics, we have a spin h bar s. So electrons, and today we are talking about electrons, not about general fermionic excitations. Fermions are characterized by spin 1/2. So projection is plus minus 1/2. So then this vector consists of three free generators known as Pauli matrices for spin 1/2. And magnetic moment of electron, magnetic moment mu is Bohr magneton S over S, where Bohr magneton is EH bar over 2 MC. So this is Bohr magneton. You know from the course of quantum mechanics that any attempt to say that electron is kind of ball and magnetic moment arising due to rotation of this little ball fail just because the fact that this magnetic moment of the electron is twice as small as the classical counterpart should be. Therefore, the spin, as you know, is entirely quantum number. Okay, then if we have a magnetic field applied to electron gas, the interaction of magnetic moment with magnetic field H. So, and I will choose z-axis such a way that it is along the direction of magnetic field. Then the Hamiltonian of interaction is very simple, is minus mu times H. So since the quantization x is chosen in the direction of magnetic field, then the Pauli matrix has a diagonal form, and we can see what happens with electron gas in the presence of magnetic field compared to the case when magnetic field is absent. So what is plotted here, what I'm plotting, is epsilon p of electron gas as a function of p. Here, magnetic field is 0. And epsilon p is, of course, e squared over 2m. We don't take into account any interactions between electrons, so we are talking about electron gas. And as I said, in the absence of magnetic field, the spin with up and down projections have the same energy. So there is no difference in energy for spin up and down, and this energy, so these states are field, so this is Fermi energy. So I plotted epsilon p minus epsilon m, if I need to put origin. Okay, what happens if we apply magnetic field? For the moment, let me also say that temperature is equal to 0, and you remember on the previous lecture we denoted mu as a chemical potential, so I want to avoid any confusion with this. Unfortunately, magnetic moment is also denoted as mu, but this is vector quantity, so I would try to avoid using confusing notations on the same picture, and for this sake we say the temperature is 0, and I'm talking about Fermi energy. Okay, what is the energy of up component? It is energy minus epsilon Fermi for up is equal to epsilon p, which is p squared over 2m, minus epsilon Fermi minus mu Bohr h. So spin is equal to 1/2. Here we also have 1/2 for Pauli matrices. So this is just addition to energy, and you see the sign is chosen to the minus, since electron is negatively charged particle. So this is what is energy for spin projection up. Let me denote, let me put a bracket here, and let me denote this quantity as epsilon f tilde up, in order to be on the same footing with our previous consideration. So this is epsilon p minus epsilon tilde f up. If we do the same for down, minus epsilon f, this is epsilon p P minus epsilon F plus mu bar H. Because down means the projection is equal to minus 1/2. Or I put a bracket, put minus here. You probably repeat this line again, and the same way I denote this as F tilde down. So this is epsilon P minus epsilon F down. So what happened in the presence of magnetic field then that is you have actually more spin up because the Fermi energy is larger than spin down. So Hamiltonian, which I would like to repeat here, is mu times H, and I would like to plot the same picture here. So on the left-hand side, I'm plotting projection up, while on the right-hand side, I'm plotting in a bit exaggerated form projection down. Of course, the chemical potential is the same, otherwise there will be current in the system. So what happens here, that Fermi energy for up and down electrons are different, just because one contains a positive addition due to magnetic field, while the second one contains a negative addition of the magnetic field. So this is epsilon P as a function of P.
Excuse me. Are we talking about quasi-electron or elementary particles?
We are talking about quasi-particles always.
So,
But you have temperature equal to 0, ground state, and nothing else. So this is a ground state property. I'm not talking about excitations at all. I'm talking about field states. So if you apply spin up, clearly there will be more electrons aligned parallel to magnetic field than anti-parallel. Therefore, your Fermi sphere, if you want to present it in the language of Fermi sphere, so this was Fermi sphere without magnetic field, which was the same for up and down projections in the absence of magnetic field. And as I said, I'm not talking about excitations at all. I'm talking about entire part of the Fermi sphere. So up, down, very degenerate. If we apply magnetic field, what we have actually two surfaces. One surface is for spin up, is a bigger one, and another surface is for spin down, is smaller one. So there is a mismatch because you have more spin up than spin down. If you switch off magnetic field, you are back to this situation. And this is what is plotted on this cartoon. So magnetic field lifts out a degeneracy in your energies for spin up and down. Therefore, magnetic field polarizes system such a way that magnetization appears in the presence of magnetic field. So you apply field, you have some magnetization. You remove field, the system is non-magnetic. The coefficient of proportionality between magnetization and magnetic field, applied magnetic field, is susceptibility. So what we will do in the next line, we will calculate magnetization, which is very simple to do, and by differentiating it with respect to magnetic field, we find susceptibility. I know that Professor Müller discussed with you a bit of a quantum or semi-classical theory of magnetism in a local fashion, in terms of phase transition. Namely, there is spontaneous symmetry breaking in the system. It is not the case. There is no spontaneous breaking of the system at all. It's just response on applied external magnetic field. You apply something, you have magnetization. You switch off field, you don't have anything. It's like, look, it's like electric current. You apply electric field, the difference of potential on two different sides of your wire. And then the current runs. You switch off your button, and there is no current. It's a linear response, nothing more. Okay. So, what is the number of electrons per unit volume characterized by projection R? I recall you that last time we introduced a quantity which is density of states, which was twice integral over d p 2 pi h bar cube delta epsilon minus epsilon p. And 2 is due to two projection of up and down. So then the total number of electrons, I recall you, is just a volume times integral from 0 to Fermi energy dE mu E. Okay? You remember when does it come from? Once I will repeat it. This is 2 times volume integral over dP over 2 pi h bar cube delta, np. So then I add integral over energy delta epsilon minus epsilon p, and use this for definition of the density of space. So as a result, it is integral over d energy, mu energy, n energy. And energy is of course positive. First of all, I put 0, but this Fermi distribution function, this step function, cuts me energy by Fermi energy because I'm accounting only field state. Therefore, we have Fermi energy and we can remove Fermi distribution function. This is how we arrive at this expression, and there is of course volume here. So, the number of particles with spin up, and now I put little n, which is total number of particles with a spin up per volume, is equal to 1/2 integral from 0 to this Fermi energy. I will write EF plus mu bar H mu epsilon d epsilon. Why 1/2? Because we defined our density of state as a sum of all projection. Therefore, if we are interested in only one projection, we need to take only half of the density of state. But what is seen here, that I plugged in the Fermi energy shifted by magnetic field, having said that there is more particle with spin up than the spin down. The same way, n down is of course n down over n, which is 1/2 integral from 0 to Fermi energy minus mu bar H mu epsilon d epsilon. And magnetization per unit volume, which is n up minus n down, can be written as should I multiply by mu bars? Yeah, mu bar. Sorry. because it is magnetic moment, and this is its mu Bohr. So it is written 1/2 mu Bohr, and when I subtract this integral from this one, I can write it down as Fermi energy minus mu Bohr h to Fermi energy plus mu Bohr h mu epsilon d epsilon. Okay? I remind you, I don't want to erase anything, that we calculated density of states for 3-dimensional electron gas this week, and it has this square root behavior and Fermi energy. So we are integrating the density of states in the limit slightly deviating from Fermi energy, and this deviation is associated with magnetic field. As I said, that in normal metals like aluminum or iron or copper, typical Fermi energies are from 1 to 10 electron volts, which is 10 to the 4 to 10 to the 5 kelvins. If you plug in all fundamental constants and recalculate magnetic field in energy units to temperature in energy units, and this is very useful when you speak with experimentalists, you will get the answer that 1 Tesla, the field of 1 Tesla, in energy units is the same, roughly the same, as the temperature of 1 Kelvin. In lab, typical fields applied to these systems is of the order of 10 Tesla. This is what can be done in most of labs doing experiments. Having fields of the scale of 50 Tesla is quite tricky and can be done only in few labs. Having fields on the scale of 100 to 200 Tesla can be done only with on a very short time scale of millisecond, just because it requires enormous currents to produce these fields on the order of 10,000 amperes. So the fields of the scale of 1,000 Tesla can be done only when you use explosion. So you see that huge fields are not accessible, actually. And when we are talking about magnetism, the best we can do is speak about fields of 10 Tesla, which is 10 Kelvin, which is nothing compared to the Fermi energy. Therefore, if we look at this cartoon, we are always in a situation of that sort. Therefore, we find to approximate our integral using the theorem of mean value as mu Bohr. Here I will put density of state at the Fermi energy. In this scale, density of state is a constant with very good accuracy, times 2 times mu Bohr h. So what I get here is magnetization, and this is magnetization in z direction, of course, because field is applied in z direction, is equal to mu Bohr square density of state of Fermi energy times h. You see, you apply field, and there is a magnetization proportional to the field applied to the system. Fine. The susceptibility, which is a proportionality coefficient between magnetic field and H, therefore it's a ratio of magnetization and magnetic field, or in the linear response definition, one can say that this is derivative of magnetization with respect to magnetic field. So chi is dm over dH is equal to mu Bohr square density of state at the Fermi energy. And I recall you the density of state at Fermi energy for three-dimensional electron gas, it's mass times Fermi momentum divided by pi squared. Okay, so we have everything. We have Bohr magneton, we have density of states, so we obtain answer at zero temperature. Okay, the last comment which I would like to do before I come to Landau diamagnetism is what happens if the temperature is not zero. Then, and I will write it here, we can proceed with the calculations the same way as we discussed the day before yesterday, take into account the smearing of Fermi distribution function due to temperature, and let me put note here, obtain the temperature corrections, which will be 1 minus pi squared over 12 temperature over Fermi energy square. So this is how temperature appears in this formula, and as long as we are at low temperatures, smaller compared to Fermi energy, we don't have to take care about these corrections because they are negligibly small. The summary is that you apply field and magnetization occurs the same direction as field is applied, and susceptibility of the system is just a constant. I recall you the knowledge from statistical physics that for ferromagnet, and we come to this point again, this susceptibility of local ferromagnet very much dependent on temperature, singularly dependent on temperature. So if you just ask the question, what is susceptibility of single spin in a magnetic field is, this susceptibility diverges as 1 over temperature. And this is known as Curie law. So if spins, local spins, are talking to each other, then the temperature diverges at some critical temperature, susceptibility diverges at some critical temperature, which is a temperature characterizing phase transition, spontaneous symmetry breaking, and this is Curie Weiss temperature. Here, we have a susceptibility is constant, and this is called Pauli susceptibility. And this constant is nothing but density of state of a Fermi gas at the Fermi level times magneton Bohr square.
And what is it? High temperature?
High temperature. This, as long as you at this regime is like that, if you are at temperatures above Fermi energy, then it's a susceptibility of the classical susceptibility of electron gas. One needs to apply the Boltzmann distribution, so it will be exponentially suppressed there. Yeah. What is important is that we are dealing with degenerate electron gas, with a quantum electron gas, and in the course of many body physics, I don't want to go and discuss classical properties. And the classical properties occur, as I said, when the temperature becomes much larger compared to the Fermi energy, and then the mean occupation number of given quantum state is exponentially small and subject to Boltzmann distribution. Okay, that's all. I will erase everything, and we start with some involved calculations for orbital magnetism and diamagnetism, and discussion of counterpart of the magnetism associated with orbital motion. But I presume that this part is known to you, because you should have discussed it during one or another course and I just repeat it using the language which I will use for discussion of orbital magnetization, orbital effects. So what I leave here is this one. Again, those who would like to look more deeply in calculation, I address to looking at Abrikosov's book, Fundamentals of Theory of Metals, where you can find more discussion, but of course less details of calculations. Because I will try to make it detailed way. Yeah. Okay. So now let's forget about spin. Spin causes shift of energy levels, and we will be talking about orbital motion of electron in the presence of magnetic field. So as you know, in the course of quantum mechanics, that in the presence of magnetic field, one needs to elongate your derivatives and replace your momentum due to gauge invariancy of the theory by shift associated with vector potential. And I recall you that in quantum mechanics, this is minus I nabla. So momentum is the differential operator. Okay, so A is vector potential, and magnetic field in the system, it's just curl of A. Again, I don't know to which notations you are used. I give you several. Sometimes in book it is written. This is one of possible notation. Another one, H is nabla times A. Another possible notation, yet another possible notation is with square brackets. Which one is more familiar to you? This one. Okay, let's use the second one. And what we are going to discuss is actually, if you look a bit classically, to the motion of electron in magnetic field. So you know that it's spiral, and we will of course discuss in plane motion, which is circular part of it, and physically what's happening. So here I already associate some trajectory with electron. Again, this is kind of semi-classical view of this motion, and just to anticipate what we can get, you see the electron moves on a kind of periodic trajectory. This is magnetic field which is applied. But electron is a negatively charged particle. Having this orbital trajectory, there will be counter field produced here, and what we can expect that susceptibility associated to this field is negative. And basically, it will have the same form, since we cannot get anything else due to dimension argument, and what we will be looking for is a coefficient in front of the susceptibility, so para. So the guess would be that diamagnetic susceptibility chi dia is first of all negative, then there should be some number which we will calculate it times mu Bohr square density of space determinant. And then, of course, the total susceptibility of electrons in the presence of magnetic field should be sum of these two contributions, and depending on what it is bigger and what it is smaller, we will get either paramagnetic metal, which is magnetized by magnetic field, or we will get diamagnetic metal. And since we know that in nature there are some diamagnetic metals, we should again think that this number can be either bigger than 1 or smaller than 1. Yeah. Okay, so now we know where to go and start to calculate. Okay, what will we do? How detailed did you discuss the quantum oscillator in quantum mechanics? Harmonic oscillator. Did you discuss it?
Yes.
Did you discuss the degeneracy of states in harmonic oscillator and the level of degeneracy? Or you just discussed wave functions and energies and that's all? Because what I will need for my calculations in the density of states for motion of electron, gas, and magnetic field, and this I'm going to derive to you. So I come through Schrödinger equation very quickly, but stop and spend some time for discussion of density of states, and then we proceed with discussion and calculation of thermodynamic potential omega and magnetization as a derivative of thermodynamic potential omega with respect to magnetic field, and susceptibility as a second derivative of thermodynamic potential omega in the presence of magnetic field. So what I'm going to do is to combine your quantum mechanical knowledge about quantum harmonic oscillator with statistical mechanical calculation of thermodynamics. I'm discussing thermodynamical effects. Okay. The Schrödinger equation, as usual, is H psi is equal to epsilon psi, and the wave function depends on x, y, z. X, y. So this is eigenvalue and eigenfunction of Schrödinger equation. Of course, I am dealing with a stationary Schrödinger equation. There is no time-dependent effect whatsoever. So the Hamiltonian, as I said, is simple. It's a free particle, so it's p squared over 2m, nothing more. But since I have a magnetic field in the system, let me use some gauge for vector potential, some specific gauge for my convenience. So H is, as you like, nabla times A. So this is vector product ort x, ort y, ort z, d over dx, d over dy, d over dz, and here it's ax, ay, az, and let me choose a in the form of 0, x, h, 0. So you see, if you plug in this shape of the vector potential, you will get h in z direction. Just because here, you probably repeated, I will put 0, x, h, 0, and the only contribution from the determinant comes along z direction. So as I said, h is parallel to E. Okay, so then the Hamiltonian in this gauge, of course, as I said, theory is gauge invariant. I can take symmetric gauge having components x and y symmetrically contributing, but it doesn't matter. As you know, non-physically observable result depends on the gauge. So this is minus 1 over 2m d2 over dx squared. This is x component plus 1 over 2m minus I d over dy squared minus e c x h squared. This is y component minus 1 over 2m d2 over dz squared. This is how Hamiltonian looks like. So you see that only x coordinate comes explicitly in the Schrödinger equation. Therefore, I can write my wave function, let's put it here, of that sort, which is a function of x, y, z, as a free motion along z direction, times e to the power I pi y y times some function of x. Because neither z or y component, coordinate component, is contained in the Hamiltonian explicitly. So now, with this ansatz and with this parameterization, I can write down the Schrödinger equation, replacing partial derivatives by full derivatives, and this is minus 1 over 2m d2 psi over dx squared. So the wave function depends on the one coordinate only. Let me take out EH over C out of the brackets. So this is plus E squared H squared, since I have squared, over 2m C squared x minus CPy over EH. So I replaced this by eigenvalue Py. Square is equal to, psi is equal to epsilon minus Pz squared over 2m psi. So what I did, I also transferred this term, which is Pz squared over 2m, to the right hand side of the equation. And let me call this as energy. So what do I have? I have equation, one-dimensional equation, which is 1 over 2m psi double prime minus there should be of course sign minus here, minus 1/2 k x minus x naught squared psi is equal to p psi. So you see that we arrived at quantum harmonic oscillator equation where the coordinate is shifted, the centrum of orbit is shifted by constant x naught. So if we will introduce new variable x minus x naught as x, and say that omega square is k over m, which is e square h square over m square c square, then we arrive at standard equation for harmonic oscillator.
It's different wavelength.
Different from what?
Different wavelength. This priming
So this is x. No. I will make this change of variables, and this only may shift the center of the orbit, and that's it. So what I'm having here is psi double prime plus omega squared x squared psi is equal to some e tilde psi. So this is the equation which I'm going to comment. I'm not going to solve it. I rely on your knowledge of the quantum mechanics. So this frequency is the cyclotron all-Larmor frequency. And what I need to subtract from this equation, that the energy spectrum is discrete, and the total energy spectrum, epsilon, this one, is equal to e square, ez square over 2m. As I said, we have a free motion along z direction. So this is z direction plus h omega c n plus 1/2. So you see that the motion in xy direction, this is x and this is y, is quantized. So instead of having continuous dependence on x and y momentum, we have a quantization of our energy occurring due to periodic motion in xy direction. And this is very important. Also, sometimes I will put h omega c, but what h omega c is equal to? H omega c is equal to eh over mc times h. So it is equal to, I put 2 and 2 here, it is equal to 2 Bohr magneton times h. So this frequency is proportional to magnetic field. So this is the same if I write pz squared over 2m plus mu Bohr h 2n plus 1. And as I said, I disregard all spin effects for the moment because spin will only shift the energy levels and nothing else. It will not change the quantization of the energies, and quantization is the main important effect I'm going to take into account. So now let me come back and comment again why magnetism is quantum phenomenon. And for example, those who would like to try with a CISA admittance exam for PhD program can find that the question about quantum nature of magnetism is one of beloved questions of examination committee. The question is why it is quantum, and the answer is, look, if you are in classical statistical mechanics, and you calculate any thermodynamic potential which will be integral over P. And in the presence of magnetic field, one can shift the variable. This is still okay in classical electrodynamics. And one can shift the variable in all integrals of a variable on the momentum, and therefore one can eliminate A from calculations immediately. Therefore, there is no response on a magnetic field in the classical theory describing orbital motion whatsoever. And there is no room for kind of orbital magnetism which I plan to derive for you today. However, in quantum mechanics, you see that the fact that we solve the quantum Schrödinger equation, we see that the motion in xy plane is quantized. Therefore, the calculation of thermodynamic potential, which we are going to proceed, will involve the integration of a continuous variable, and continuous variable described as free motion along z direction, and summation of a discrete variable. So no shift can be done, and therefore the non-trivial contribution to magnetization and susceptibility appears. So the quantum nature of orbital magnetism is associated with discrete discretization of a spectrum, and of course, as you know, the first look to see whether the effect is quantum or classical is to look for h bar, and since h bar is there, so we are on the safe side. Okay, I erase everything and discuss Landau levels and degeneracy of Landau levels, the discretization of spectrum and quantization of the motion in xy plane leads to Landau some energy levels, and these energy levels are known as Landau levels. And what I'm going to discuss in the next 5 minutes, probably I have to change gear a little bit, is the density of states. Is it clear logically what we do, why we do, and what we are going to obtain? Okay, let's assume that we have box, piece of metal, with a size of L1, L3, L2. So if we solve our Schrödinger equation for non-interacting particles in the absence of magnetic field in the box, we will find some energy levels, discrete energy levels, and discreteness is associated with the final size of your well. Okay, what we see there is we have Landau levels which are degenerate and which accumulate some levels, and quite a lot of them associated with the free motion in xy direction. The motion in xy direction is not free anymore, so the motion is periodic one. So the question is,